So yesterday we were talking derivatives of log functions. Let's just try a few more of those. So what about one like this? Is there any way to compress this, or I not compress, any way to make this one easier? So there's a fraction there, right? But remember our property of logs that deals with fractions. It doesn't really apply here, does it? We know that the log of a divided by b equals log a minus log b, but that's not what we've got going here, is it? Right? So this one, unfortunately, I mean, does everybody see that there's nothing we can do to that? We're just stuck with that the way it is, right? So we would have to just power through this using the quotient rule, right? So what's that give us then? Okay, so the natural log of 4x plus 1, low d high, right? That's low. Times what's d high? Two x over x squared minus 1. Everybody agree? Right? Because that's the derivative of log u, remember, is u prime over u, right? So u prime is going to be 2x divided by u. Everybody good with that? So there's low d high minus high d low. What's d low going to be? Divided by low squared, which we're stuck just squaring that whole quantity, right? So we end up with natural log 4x plus 1 squared, and it's a mess, but that's what we get. And we won't even bother cleaning it up. I mean, there's really not a lot we can do to this one. It's going to look ugly no matter what we do. We could maybe get a common denominator, on the top, and yep.
Would you be able to cancel that other log 4x, or is that just?
Well, what do you think? You guys answer that question. Could we cancel a log 4x plus 1? I'm seeing people shaking their head. That's right. How come you can't? It's not a factor of the top, right? It's only in one term. I'd have to factor something out of both terms, so it's a factor of the entire numerator to be able to cancel it. Does that make sense? Okay. All right, so that one, I mean, we're just stuck with a horrible answer on that one. Okay, so mentioned this yesterday, right? So we know that if we can write this derivative sometimes as the derivative with respect to x of the log of the absolute value of u. We do that sometimes to ensure that we're feeding positive values to the log function, because it's only defined for positive values, right? That's the domain of any log function. And it doesn't matter. The outcome's the same. It's just u prime over u. So let's just try maybe one of these real quick just to kind of make sure we're got this figured out. So nothing I can do to simplify that, right? What's that going to give me? Cosine x over sine x, which if I want to, I could even write as cotangent x. Okay, make sense? u prime, the derivative of sine is cosine over u prime over u, right? It's just then cosine x over sine x. Okay. How about this guy? Is that one I could make easier? Could I use properties of logs there? I can I, right? How come? Because I've got a log of a knot of exponentials and products only. There's no sums or differences, right? It's just stuff that's being multiplied and exponentiated, and that's what properties of logs are good at. That's where they can really come in handy. So I've got a product of 7 times cosine squared, so I'd get the log of 7 plus the log of cosine squared. Well, cosine squared x means cosine x squared, right? So I could pull the 2 out front, and I could simplify that quite a bit. That's going to be a lot easier, isn't it? If I were just going to power through this thing, it would be kind of an ugly derivative, right? I'd have to do u prime on the top. Well, the derivative of 7 cosine squared x would be what? 14 cosine x times the derivative of cosine x, right? Everybody see that? Because I've got 2 layers there. I've got the derivative of hand squared is 2 times hand, right? So there's my 14 cosine x times the derivative of cosine x is going to give me a minus sine x, right? All divided by u, which is 7 cosine squared x. Okay, Jonathan, can I cancel a cosine there? I can, you're right. Okay, I could cancel one of those guys. And so we'd end up with our answer being negative 14 sevenths. Well, that's just negative 2 sine x over cosine x is just tangent x, right? Okay, give me thumbs on that. Does that all make sense? Okay, good. Wouldn't that be easier over here, though? I mean, way easier, right? Over here, if I were going to differentiate that, derivative of log 7 is what? What is it? Which is what? 0. And we know it's 0 because log 7 is a constant, right? That's just a number. So the derivative of a constant is 0 plus 2 times the derivative of log cosine x. Well, that's just going to give us derivative of cosine is negative sine, right? So I'm going to get my negative 2 sine x over cosine x, which is just that, but way easier, right? Okay. All right. Maybe I can't remember if I have any more of these. No. Okay. So we're warmed up. Now, what about this guy? We've done some stuff like this before. I think we tackled one like this when we were learning quotient rule and product rule. And it was pretty tough, right? That's going to be a quotient rule problem, but in the numerator, we've got a product, right, that also involves chain rule. So we can do this one the long way by using quotient and product rules, embedded quotient and product rules. But it's a lot of work. I've got to simplify it all out, and I've got to factor out least common powers, et cetera, et cetera. And we've had some experience with that. Okay, is there a better way? Now think about what the properties of logs did for us. They did some good things, right? They made arithmetic connections simpler. We moved one rung down the order of operations tree, right? Could we take advantage of that here? What's the problem with this? Why is this not automatically a logarithm problem that we could use properties of logs? What is it? There's no log, right? But is there anything preventing us from taking the log of both sides? No, nothing, right? We can do that. That's fair game. As long as I treat both sides equally, that's fine in an equation. So when we see problems like this, where I've got some function that's a big tangle of products and quotients and powers, that is just tailor-made for properties of logs to simplify, right? Then we're going to employ a technique called logarithmic differentiation, where step one is we take the log of both sides in order to harness those, the properties of logs to our advantage, right? So what happens if we do that? So if we log both sides, and we'll just use a natural log, we get the natural log of y is equal to the natural log of all that stuff. Okay, so there's a lot we can do with that. You guys are getting pretty good at your properties of log stuff. So untangle the right side for me, please. What's that look like? Tori, start us out. Okay, you're right. You're going to pull that 3/2 down there. But first, before you do the power, we got to think, are there any products and quotients there? Because remember, we've got some properties here. Let me remind you about a couple properties. The natural log of the product of A and B is natural log A plus natural log B. Natural log of the quotient of A and B is log A minus log B. And the natural log of A to the n is n log A. So there's our properties, right? What do you think? You see a way to, how are we going to untangle this here? That help? Kind of, okay. Okay, so what you're thinking? Just talk to us about it. Okay, so you're wondering, does that 3/2 come out in front of everything? Okay, what's the answer to that? Anybody know? No, I'm going to have to separate it first, right? So what's the first step going to be? Becca, what's the first step going to be then? Okay, so I get the log of the top minus the log of the bottom, right? Okay, so what about the log of the top? While I'm at it, what could I do to the log of the top? Okay, yeah, I've got a product of x times this power, right? This other one. So that's going to give me log of x plus the log of that one. Now, Tori, what's the log of that piece going to be right there? There you go. 3/2 times the log of x minus 1. And then minus the log of the bottom, right? Okay, Jonathan, what's the log of the bottom going to look like then?
So would it be 1/2 log and then whatever u is, so x plus 1.
There you go, right? Okay, everybody good with that? Does that make sense? Okay, that still kind of looks somewhat bad, but not nearly as bad as what we started with. Yes, sir.
When you say natural log, like,
Hmm?
a lot of people be saying natural log.
But the ln is natural log.
It is natural log. Yeah, and okay, so mathematicians, they just a lot of times get lazy and just say log. Yeah, if we know we're dealing with natural logs, you just call it a log. It's just too hard to say natural log every time. Just, but yeah, I mean natural log. Yep. It doesn't make any difference. This is the easiest one to write. It's the most common one that we use. So I would always use natural log. Yeah. Okay. Make sense? Okay. So now what? We're trying to differentiate. What do you think? Got an idea? Oh, question. Yep.
So for ln, does it also have a base of 10?
No, natural log has a base of e. Yeah. Mm-hmm. But we don't have to write the base. That's one of the reasons you pick natural log. And the other reason we pick natural log a lot is because it's arguably the most useful. We're going to look at some applications of the calculus of logs, some transcendental functions later on, and you'll see that a lot of the really interesting stuff you can do that relates to nature involves natural logs. Okay. Now what? Remember, we're trying to differentiate this thing, right? We're trying to find y prime. So now what? Differentiate how? How would you describe that? What we're doing? What would we call this process in math? Yeah, we're going to differentiate implicitly with respect to x. Yeah, because we want y primes, which are dy dx's, right? Good. So that's how we would describe this step then. Implicitly differentiate.
So in the first step, we expanded.
We logged both sides. Yeah. And now we're going to implicitly differentiate with respect to x. So what does that give us on the left side? What's the derivative, Max, what's the derivative of log y with respect to x? Mm-hmm.
Y prime over y.
Yep, makes sense? Yeah, right? Because the derivative of, what's the derivative of log u with respect to x? U prime over u. Well, what's the difference between y and u? I mean, it's just trading one for the other, right? So y prime over y equals, what's the derivative of log x? Liliana, what's the derivative of log x? Yeah. Mm-hmm. Okay, it's just going to be the derivative of log u is u prime over u, right? So it's going to be the derivative of x divided by x, right? What's the derivative of x with respect to x? Yeah, just 1. Yeah. So that's just 1 over x for that one, right? That term. Okay, Olivia, next term. What's this going to give us? What's the derivative of log x minus 1? Over x minus 1. And then we'll multiply by 3 halves. So we'll have 3 over 2 times the quantity x minus 1 when we multiply by the 3 halves. And then last one, what's that going to be? So what's the last derivative going to be here? Derivative of log x plus 1. There you go. 1 over x plus 1 times 1/2 puts that 2 on the bottom. Good. So minus 1 over 2 times x plus 1. That wasn't so bad, right? Then all we have to do now to solve for y prime is one step. What's that? Multiply by y. Yeah, that's it, right? Multiply each side by y, and we get y prime equals all this stuff times y, which is that, right? Y was defined for us at the beginning. It's ugly, but that's what it is. So it was x times x minus 1 to the 3 halves divided by square root of x plus 1. There's our answer, our big ugly answer. Yeah. That's why I have to put the whole thing in parentheses or brackets, right? Well, because I'm multiplying the whole thing by y. I have to get this y on the other side. All this is right here, right? This whole thing is just y. Yeah, I got to isolate the y prime. Okay, and that's probably how we just leave it. I mean, you could, if we really wanted to clean this up, I could add these fractions up, get common denominators, and add the fractions up. But, that's probably not that big a deal. Okay. Make sense? So logarithmic differentiation. Again, what's this process? Let's just review this real quick. So we use this when I've got a function that's amenable to properties of logs, right? Where I don't have any sums and differences. All I have are products, quotients, and powers. That's when properties of logs are helpful. Okay? Okay, what about one like that? Thumbs up or down? Can I use logarithmic differentiation? Well, everybody think about it for a second. What do you think? Can I use logarithmic differentiation? Okay, why'd you change your mind?
Because there's subtraction.
There's subtraction, yeah. And remember what properties of logs do, right? They take the PEMDAS tree and they move exponents down to products. They move products down to sums, differences down to, or division down to subtraction. But there's no place, if I start on the bottom of the ladder, there's no place to go, right? So I can't have addition or subtraction. So because of this, the answer is no. Okay. What about that one? Could we do that without logarithmic differentiation? Do we have any rules for that? What do you think? Chain rule? Okay. Yeah, but what you're going to use chain rule with what rule though? You still got hand to the 2x. See what I'm saying? We don't have a rule. It's tempting to want to apply like the power rule to this, right? To bring the 2x down front and subtract 1 from 2x, but that doesn't work. That only works for, we derived that rule, but that rule only works for powers, for power functions, where we've got a variable base to a constant power. This is different. This is more complicated. We don't have a rule for this. There is no derivative rule. So we have to use logarithmic differentiation here. It's the only way to do this problem. So we'd log both sides. And what's the advantage of that? What's the property of logs that's going to apply here? The exponent rule, right? I can bring the exponent down in front of the log. So this, I can rewrite this then as log y equals 2x log x. And now that's manageable. So what am I going to do next? Okay, more specifically, I'm going to implicitly differentiate with respect to x. There we go. Okay, so that's going to give us, from this first one, I'm going to get what? Y prime over y equals, how about over here? Let's group it like that. How about? How am I going to differentiate the right side? Okay, I got to use product rule, don't I? Right? So I'm going to get 2x times the derivative of log x, which is 1 over x, plus log x times 2. Right? Does that make sense? Okay. We could simplify that a little bit. So we get the 2 and the 1/2 are going to, or sorry, not the 2, the x and the 1 over x cancel, right? Those guys cancel. And so if I multiply each side through by y, I'm going to get y prime equals 2 plus 2 log x times y. And what was y? Y was originally defined as x to the 2x. And I guess we could pull a 2 out of that also. Yeah.
I still don't see how it's not possible to differentiate x to the 2x.
X to the 2x, like using which rule?
Yeah.
Power rule? Well, let's try it. Let's see what we get. So if we try that, if we try to just differentiate this with the power rule, we would get y prime equals 2x times x to the 2x minus 1. Is that what we ended up with? No. That's not what we ended up with. Okay. How am I going to do chain rule when you see that I can't do chain rule because I don't have a pattern for it. You see what I'm saying? Yep.
I just have like a guess, not a guess, but like I was just curious. Can you do the product rule on to the exponent? So let's say you can do the derivative of 2 and then
You can't. You just can't do it that way. The only way to do this is you have to use logarithmic differentiation. And here's a clue to why that's the case. What appears in your answer that otherwise wouldn't? A log. Yeah. Okay. So I guess if we wanted to write this, we can go one more step maybe and say if I factored out a 2, I could say 2x to the 2x times 1 plus log x. But that would be about as far as I could go. Okay? Make sense? Okay, I think I'm going to stop there and let you catch up a little bit, and then we'll move on with some new stuff. Well, we'll see about tomorrow. See what you can do. Yeah, there's